So in this lesson, we're going to take a look at the dot product, which is the first of the two types of vector multiplication that we're going to look at in this unit. So we're going to start off by having a little preamble here about basically what it means to multiply vectors, put it in context of types of multiplication that you've done before. And then we'll look at how you find the dot product or the scalar product of two vectors if you're given the vectors as geometric vectors, so as arrows or with magnitudes and angles and things like that, and then we'll take a look at how you do it if you are given them in algebraic form. So basically as those ordered pairs or those ordered triples that we were looking at earlier in this unit. And then finally, you guys are going to, in the practice questions, use the properties of the dot product to solve problems involving vectors. So multiplying vectors. We've got two vectors up here. We've been representing these as arrows with a magnitude and a direction. What does it mean to multiply two things that are just like these arrows pointing in different directions? What we're going to find is that the key to multiplying vectors is what we decide to do with the directions. We're familiar from like years and years and years ago how we treat things if we have two things that just have magnitudes, basically two scalars that we want to multiply together. If we've got something of magnitude 2 and something of magnitude 3, we just multiply the two magnitudes together and we get the magnitude of the answer, which is also a scalar. What do we do if these numbers, though, have directions associated with them? We've already looked at one kind of multiplication here involving vectors, and that is scalar multiplication. So when we're doing scalar multiplication, we were taking some vector, let's say vector v, and we were multiplying it by a scalar, something like 4. So let's say we're multiplying these two things and we're getting some new vector w. In this case, it was kind of clear on what we did with the direction. We have something with a magnitude, that's our scalar here. We have something with a magnitude and a direction, that's our vector here. So with only one direction to work with, we just kept that one direction and we used it as the direction for our new vector w. So mathematically, we did something like kept our scalar and we thought of this vector v as having the magnitude of v and then the direction of v, which we represented using the unit vector. This whole thing here is vector v, and then we said, okay, to get our new magnitude, we're going to multiply our 4 and our magnitude of v together. This will be the magnitude of w, and for our direction, we just kept the direction. So vector w was a vector that was 4 times longer than vector v in the same direction as vector v. And to create an analogy here, this is kind of like what you did way back when you first started learning how to multiply algebraic terms. If you had something like 2 times 3x squared, you said, okay, that 3x squared has a coefficient and it has a variable. What do? Well, I only have one variable part, so I'm just going to keep that variable part exactly the same. And then I'm going to multiply these two numbers together to get something like 6x squared. If we're multiplying two vectors together, it's more like doing this kind of algebra question, where we have two things that both have a coefficient and a variable, and we want to multiply them together. When you did this kind of multiplication, you took the coefficients and you multiplied them together just like you did before. But to combine the variables, you had to sort of treat them a little bit differently. You kind of had to think of x squared as being something that represented an area, and then x as being something that was a length. So if you had an area and then a length, you could arrange them to get something that instead of being 2-dimensional was 3-dimensional. So this gave you something like x cubed. So slightly different rules that you had to follow when you were dealing with the coefficients and when you were dealing with the variables. We're going to look at two types of vector multiplication here. What are called the dot product and the cross product. And how they differ is how they get you to treat the directions of the two vectors. And there's a couple of other differences as well. For the dot product, we're going to use the symbol dot. Okay, makes sense. For the cross product, we're going to use the standard multiplication symbol. Okay. Now, up until this point in your mathematical career, these two symbols have meant exactly the same thing. It means multiply the two things that you have. But when we put vectors on either side of them, they now mean different things. The dot now means do the dot product. the multiplication symbol now means do the cross product. Another difference between these two is the dot product is also called the scalar product, because when you do the dot product of two vectors, you don't end up with another vector, you end up with a scalar, just a pure number. Whereas the cross product is also known as the vector product, because when you do the vector product or the cross product of two vectors, you end up with a third vector as your answer. So dot product gives you a scalar as your answer, cross product gives you a vector as your answer. The final difference is how they get you to think about the directions. The dot product is interested in multiplying the parts of the vectors that are parallel to each other, whereas the cross product is interested in getting you to multiply the parts of the vector that are perpendicular to each other. What does that mean? Well, if we understand what that means, that goes a long way towards us figuring out how exactly do we do the dot product and how we do the cross product. So let's look at the dot product. Here is sort of a summary of what you need to know about the dot product. And we're going to start by thinking about it in geometric terms. So we're given two vectors here, vector A and B, and we're given the magnitude of A and the magnitude of B. A has a magnitude of 5, and it has a direction of 53.1 degrees to the positive x-axis. Vector B has a magnitude of 7, and it's at a direction of 0 degrees to the positive x-axis. The formula for the dot product is up here at the top in the red box. If I want to do the dot product of A and B, so A dot B, it's going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. So we imagine vector A and vector B place tail to tail. We want to know the angle between these two vectors. Well, in this case, it's just going to be the 53.1 degrees. That's the direction for A. So if we're working out down here at the bottom, A dot B, we can just use that formula. Magnitude A, magnitude B, cos theta. We know that the magnitude of A is 5. The magnitude of B is 7. The angle between them, and they're placed tail to tail, because we always want the angle when they're placed tail to tail, is 53.1 degrees. And we just sort of punch this into our calculator, and we end up with 21. So the dot product, A dot B, is equal to 21. Scalar product, because our answer here is a simple scalar. Okay. Now, what does this actually mean? If I take this formula here for the dot product and I rearrange it a little bit, so instead of A, magnitude B cos theta, I write it as magnitude A cos theta magnitude B, we can think a little bit about what this means. So if I think of what magnitude A cos theta represents, back in the previous unit when we talked about components, we said that, okay, if we take the magnitude of the vector times cos of the angle, we're going to get the component of the vector that's in the horizontal direction. So that would be this vector right here, magnitude A cos theta. So my dot product here, magnitude A cos theta times magnitude B, is saying take the part of vector A, which is in the same direction as B, and only that part of it, and then multiply that by the magnitude of B, okay, which is what it says right up in here. So this is how the dot product kind of represents parallel multiplication between these two things. Okay, so that is how you do the dot product if you were given geometric vectors. Now, what if instead of giving us geometric vectors, they gave us these two same vectors as algebraic vectors? The vector A as being 3, 4, and the vector B as being 7, 0. Well, let's take a look at algebraic vectors here. Here I've got two different vectors, A and B. A is 7, 5, negative 2, and B is negative 3, 8, 1. To do the dot product of these two, A dot B, what I'm going to do is I'm going to look at my x components, so 7 and negative 3, and I'm going to multiply them together. to this, I'm going to add my two y components, so 5 and 8 multiplied together. And then I'm going to take my two z components, multiply them together, so negative 2 times 1, and add that on. So my x is multiplied, my y is multiplied, my z's multiplied, and then I add everything up. So what do I get here? I get negative 21 plus 40 minus 2, which gives me 17. So again, my answer is a single scalar, single number, okay, as befitting our scalar product. So let's return to those two vectors that we had on the previous slide. A is a vector 3, 4, B is vector 7, 0. I can do the dot product the exact same way. A dot B is going to be, let's see, my x is multiplied together, so 3 times 7, plus my y is multiplied together, so 4 times 0. 3 times 7 is 21, 4 times 0 is 0. I get the dot product of A and B is 21, just like I had on the previous slide when I did it using the geometric vectors. And that is the dot product.